The story of Earth's formation is a tale that began long before life, continents, or even a solid crust. It's a story rooted in the chaotic early days of our solar system, where dust and gas swirled around newborn CERN, gradually coalescing into planet. But what really happened when Earth was just a tiny ball? How did this tiny ball, nascent sphere of molten rock, evolve into a complex, life-sustaining planet we call home today? This journey of Earth from a tiny, fiery ball to thriving world we inhabit is nothing short of miraculous, filled with cataclysmic events, intense heat, and gradual cooling. Watch this video till the end to know how Earth was formed from a tiny ball. About 4.6 billion years ago, our solar system was a vast disk of dust and gas orbiting the young sun. This protoplanetary disk was the birthplace of the planets, including Earth. The process began with the tiny particles of dust and ice sticking together through electrostatic forces, gradually forming larger clumps. Over time, these clumps collided and merged to form planetesimals, small solid objects that could be several kilometers in diameter. As these planetesimals collided, they released heat. This heat, combined with radioactive decay of elements like uranium, thorium, and potassium, caused the young Earth to become a molten sphere. At this stage, Earth was far from the hospitable planet we know today. It was a small molten ball constantly bombarded by other planetesimals and even protoplanets in a chaotic environment of the Earth solar system. But as Earth grew through acceleration, the increasing size and heat led to a crucial process known as planetary differentiation. This process involved the separation of Earth's material based on their density. The heaviest elements such as the iron and nickel sank towards the center, forming Earth's core. Meanwhile, the lighter elements like silicon, oxygen, and aluminium floated towards the surface, creating the mantle and eventually the crust. This differentiation was a violent and dynamic process. The sinking of heavy elements generated even more heat, which kept the early Earth in a molten state. The formation of the core also generated a magnetic field, which played a crucial role in protecting the young planet from the sun's solar wind, allowing the atmosphere to form and remain intact. One of the most dramatic events in the Earth's early history was the formation of the Moon. According to the widely accepted giant impact hypothesis, around 4.5 billion years ago, a Mars-sized body, often referred to as Theia, collided with the early Earth. This catastrophic impact was so powerful that it ejected a massive amount of debris into space, which eventually co-escalated to form the Moon. This event has a profound effect on the young Earth. The impact likely caused Earth's axis to tilt, which is why we experience seasons. It's also increased the planet's rotation speed, shortening the length of a day. Additionally, the formation of the Moon helped stabilize Earth's axial tilt over long periods, preventing drastic climate change that could have hindered the development of life. The period following the formation of the Moon is known as the Hadean Aeon, named after Hades, the ancient Greek god of the underworld. This aeon, which lasted from about 4.6 to 4 billion years ago, was a time when the Earth was still a hellish environment, with a molten surface, frequent volcanic eruption, and a constant bombardment by asteroids and comets. During the Hadean, Earth's surface began to cool, allowing the formation of a solid crust. However, this crust was likely very thin and fragile, frequently broken up by ongoing volcanic activity and impacts. Water vapors and other gases released by volcanic eruptions contributed to the formation of Earth's early atmosphere, which was very different from oxygen-rich air we breathe today. Instead, it was likely dominated by carbon dioxide, water vapor, methane, and ammonia, making it a toxic and hostile environment for life as we know it. Despite the hellish condition, Earth's surface gradually cooled enough for water to begin condensing. The origin of Earth's water are still a topic of scientific debate, with two main theories in contention. One theory suggests the water was delivered to Earth by icy comet, an asteroid that bombarded the planet during its early history. Another theory proposes that the water has already present within the Earth's mantle and was released through volcanic outgassing. Regardless of its origin, its accumulation of water on Earth's surface eventually led to the formation of the first ocean. These early oceans were very different from today's sea, possibly acidic and teeming with dissolved minerals from the young Earth's crust. The presence of liquid water was a crucial milestone, setting the stage for chemical processes that eventually led to the emergence of life. Around 4 billion years ago, Earth entered the Archean Eon, marking the end of the Hadean Eon and the beginning of a more stable period in Earth history. During the Archean, Earth's crust has cooled and solidified enough to support the formation of a stable continent, although these land masses were likely much smaller and different in composition compared to today's continents. Most significantly, the Archean eons witnessed the emergence of life. The exact origin of life on Earth remains one of the scientists' greatest myths, but it's believed that life begins in the oceans, possibly in deep-sea hydrothermal vents, where chemical reaction provided the energy needed for the first simple organism to form. These early forms were very simple, single-cell organisms known as prokaryotes. Despite their simplicity, these organisms were incredibly important as they began the process of photosynthesis, a process that would eventually transform Earth's atmosphere by producing oxygen as a byproduct. This gradual increase in atmospheric oxygen is set stage for more complex life form to evolve in the eons to come. Following the Archean Eon, Earth entered the Proterozoic Eon, which lasted from about 2.5 billion to 541 million years ago. This eon was a time of significant geological, atmospheric, and biological changes, laying the groundwork for the expulsion of complex life form that would follow. One of the most important developments during the Proterozoic Eon was a Great Oxygenation Event, GOE, which occurred around 2.4 billion years ago. The rise of photosynthetic organisms, particularly cyanobacteria, led to a dramatic increase in the amount of oxygen in Earth's atmosphere. This event was both a blessing and a curse. While it allowed for the evolution of aerobic, oxygen-breathing organisms, it also caused a mass extinction of many anaerobic, non-oxygen-breathing organisms that could not survive in the new oxygen-rich environment. The Proterozoic Eon also saw the formation of supercontinents, large landmasses that periodically formed and broke apart due to plate tectonics. One of the most famous supercontinent, Rodinia, formed during this time. The breakup of Rodinia likely played a role in triggering the Snowball Earth event, periods when the entire planet was covered in ice. Despite the harsh condition of the Snowball Earth period, life continued to evolve. By the end of Proterozoic Eon, the first multicellular organism had appeared, paving the way for the expulsion of life form that would define Phanerozoic Eon.